In the last section, we studied finite difference methods. In this section, we'll apply them for differential equations of non-constant diffusion coefficients. Let's look at this equation. For this term, we rewrite here p y prime rather than sub x. We are using prime notation. That can be written in this way by using the product rule of derivative. Here, that is p y double prime plus p prime y prime. Once p is differentiable, this term and these two terms will be the same, exactly the same. In mathematics, they are the same. However, we are trying to get approximate solution with a certain error. Right now, we are using 30-point difference formulas so that we have second order error. When they are approximated, then the solution from here may not be the same. In physics, y prime, that is related with convection, movement, so that the solution from these terms will be a little bit different and will have a little bit of sense of movement, so that the solution accuracy may not be reaching at this level. So we'll see example later on. Here, we'll try to approximate this term directly. But the manner of solving this problem is, again, the same. There are 4 steps. Step 1, we partition the domain. And in second step, we'll try to recognize unknowns and how we can get unknowns. And in third step, we'll try to gather difference equations. And finally, out of these difference equations, we'll try to get algebraic system A, V equals B. Okay, let's go step by step. Step 1, partitioning. Exactly the same way. We try to partition the given interval A to B into n equal subintervals, so that in the beginning, A to B, there's A, that is now x0, and there is x1, x2, and so on in this way. So last one will be xn, which is B. That is a partitioning. Okay, so we split the zone. In the second step, we try to find a difference approximation by using central find a difference scheme for this term. And along with this one, we just recognize the unknown. For this non-constant coefficient, the diffusion term, we start with this one, p y sub x, p y prime, this one as a function. And then we try to get approximating first for that function. So here, pictorially, we can explain this way. Now, this point is xi, and left point is xi minus 1. Right nodal point is xi plus 1 at xi. Now this is the focal point for this function. At the point, we try to approximate the derivative of that term by using here this point, the midpoint, and midpoint here. So from here to there, we are trying to make approximation. So that is exactly this one. For the function, py prime at the point minus the function at this point. The length is h, so divided by h. This is a central scheme having second order error. Now, for each of this one, we'll try to approximate it. Of course, right now, these values are not available. And in fact, now we try to get unknown at each nodal point, not this midpoint. So anyway, this is intermediate term, and we'll try to approximate it. Okay, so for example, right now, for that term, okay, at this point, this one is involving derivative, and so that for p we evaluate immediately, but for that term, derivative we can approximate along with this central scheme and divide by h, so that for the function at this point we try to make from here to there, from here to there. So it's a distance h. This is again central scheme having second order error. For the other term, this one, we can do similarly, and we try to combine them. Then, now, from here we are using this portion, from here we are using that portion, and we are ignoring this part, and here we have that. Now, the question is, originally we have h on the bottom. These are second order approximation. So ignore the term on the top is a second order divided by h. But here, and one more h comes here, h squared. Then maybe apparently probably first order. However, by using some careful mathematics, even though the discarded terms have a second order and divided by h, eventually, because this one subtracted later on by that, this result will be third of the term and divided by h, so end up with finally second order error. So we can reach this formula and second order error. For this mathematics, I gave you a hint and try to figure the mathematics out yourself. In exercise 1, you will do it. So we have this formula, and the values, the approximated values, will be obtained through this approximation scheme. Okay, so that is. Also, one more thing is that here, pi plus half, and that is, you can, now, for example, for this point, you may try to average them. Sometimes your coefficient is not given as a continuous function. Only at grid points the value can be given. Then you may average this value, that value, and so that you can get the value at this midpoint. That is one way of doing this one is arithmetic averaging or harmonic averaging. That is first, take a reciprocal of the quantities and average them, and then finally take a reciprocal. That is called harmonic averaging. And in practice, if you are doing this way, then it is better. And mathematically, we can prove that along with this approximation for this value, we can prove that the flux is conserved. So for this intermediate value, you can use that. That is better than this simple arithmetic averaging. Anyway, in this second step, we recognized unknowns, and unknowns will be related with this formula. Okay, here in third step, we'll try to gather finite difference equations. Now, along with approximation, even though we are using y notation, anyway, for this one, right now, the error on the right side, and once it's eliminated, then that will be approximated value. Okay, this is a scheme, and at y0 again, at the left edge point, already alpha is given, and when I is n, right edge point again, we have the issue of dealing with the outside value. This is yn, and so that from here first we consider outside yn plus 1 is given, and then we try to eliminate by using the boundary condition at this point. Okay, that is the values yn, the xn equals b. Right? Exactly same way as in the earlier case, in the last section. So we try to use this approximation for yn plus 1. Okay, so we gather equations, and along with this one, now here, and we put together, and when I is 1, we have this equation. When I is 2 to n minus 1 interior points, and then we have this approximation. And when I is n, we have this one. Of course, this one is coming from the extra equation from boundary condition. Okay. And here we reach this algebraic system, and A is given this triangular, this three-diagonal metric, and B is two parts. One is from the source term, and these are from the boundary conditions. So we got an algebraic system. By solving this algebraic system, we can get the approximated value u. So that's how finite difference method is working, even though the coefficient is not a constant. Okay, let's see this example. Early in the last section, we solved this problem, and along with at one left edge point, the function value is 0, and at the right edge point, the derivative is minus 2. For this problem, the exact solution is this one. Now, for these two terms, rather than y double prime and y prime, now we try to divide by x the equation, then these two terms can be written into this one term, so that now this equation is changed into this form. So that will be p, that's y prime and prime. So it becomes a non-constant diffusion quotient problem. So we'll try to solve this one. However, this one is the same as this equation. Okay. Now, once we implement a code and get the solution, then we can see here. Now, that one is from earlier example. In the last section, I copied it, and this one is new solution when h is 1/5 and when h is 1/10. Look at here, error. Let's try to compare error. And this one is about 0.1 error, but it's a little bit smaller, right? And you can see really everywhere and now a little bit smaller. In the second order approximation, this term basically now that term will try to give some convection phenomenon so that the solution will be a little bit deteriorated. So accuracy is lower. When you deal with a little bit more complicated problems in higher dimensions, then solving the problem in this way is not a good idea. Once original problem is given in this way, then don't expand. Just try to solve this problem as given. Okay? Here we have a remark. Once differential equation is given in this way and assuming P is differentiable, then you can write this one in this form. But here, occasionally, and this one makes much worse numerical solutions, and particularly when the diffusion function P is oscillatory or non-smooth. And changing this way means that we have to assume that P is differentiable and also smooth, but it's not smooth or sometimes oscillatory. Then if you try to work with this equation, then your solution will be much worse, particularly when you are dealing with finite element method. Then you have to keep using this equation. Try to approximate this one rather than this one. Okay. That's the end of the section. Thank you.